Welcome to the Cine webinar. My name is Pablo Fernandez. I am professor of the State University of Campinas. Today is my pleasure to introduce you to Professor Caue Ribeiro de Oliveira. Caue, engineer. I will start with a brief presentation. Caue, thank you very much for being here. Caue is materials engineer and PhD in physical chemistry from the Federal University of São Carlos in 2005. He is senior researcher of the Brazilian Agricultural Research Corporation, Embrapa. He's author and co-author of more than 200 scientific papers. Caue research includes semiconductor synthesis and photocatalytic application, and slow and controlled release system for the delivery of agricultural inputs. Today, the presentation title of Caue is a perspective view of photoelectrocatalysis application in agriculture. Well, before starting, I want to remind you to do the inscription in our Cine channel, and then do not hesitate in asking questions, both in English, and if you prefer, you can ask in Portuguese. Well, thank you very much again, Caue. Feel free to start.
Thank you so much, Paulo. Thank you so much, everyone from Cine Events Organization. I am so happy with the opportunity to talk to you today about this topic that we are doing research during the last 15 years. In the last 15 years, we are doing in several of these topics, these possible applications, research about the photocatalytic applications in agriculture. Agriculture is the topic that we are more interested because we are an institute devoted to the research for in agriculture in Embrapa. I will talk a little bit about my institute after. But that idea of agriculture and catalysis is so old, more old than we can imagine. Actually, the nitrogen fertilizers in general, all the nitrogen fertilizers that we are using in the world today, they are produced by the Haberbosch process, which is a process that developed in the beginning of the 20th century to reduce the nitrogen, the atmospheric nitrogen, using hydrogen and producing ammonia. This ammonia can be used as a building block for several products, main products that we have nowadays. But most of them, this ammonia is used to produce fertilizers, and these fertilizers are critical for the survival of the humankind today. This process is typically catalyzed by iron-based compounds that have been developed by Fritz Haber and are the key that can hold can hold this process to make this as a viable process. So the consumption of fertilizers today is really remarkable in terms of size, but more interesting to understand this is to see how many people are fed today by fertilizers, by synthetic fertilizers. Most of the almost 0.5% of the population, the human population in the world today is supported by the utilization of these fertilizers, the synthetic fertilizers. So the importance of these fertilizers is really remarkable, is really outstanding. We cannot survive without them. At least in the size of the humankind as we have the population as we have in the world today. But the idea of why photocatalysis is still obscure in our mind. Naturally, using solar light to drive a reaction seems to be naturally interesting because we are using widely available kind of energy to produce these reactions. But on the other hand, how to do this? The most important part of the photocatalysis lies on the property of many semiconductors. For instance, almost all the semiconductors that all oxides that we can produce, but not only oxides, when they are irradiated with proper wavelength, they have the production of a pair, electron hole pair, that can be used for to produce reactions in general. For instance, we can use, for example, the titanium oxide, which has a 3.2 electron volt band gap. When this titanium oxide is irradiated with UV light, this electron can perform some reduction reactions, while this hole in the conduction in the valence band can produce can perform other oxidation reactions. The most important, there are dozens of different reactions that can be explored. For instance, you can see a list of different reactions that can be performed by the irradiation of semiconductors, and the requirements depend. The requirements are the transference of this electron to the surface to produce a reaction, reduction reaction, and the transference of this hole to the surface to produce an oxidation reaction. Among these main reactions that we can explore over these catalysts, specifically, we have two of higher interest. For instance, the oxygen evolution by water, the water oxidation to produce oxygen, and the second one is the oxidation of OH OH minus in water to produce OH radicals. These OH radicals are really are very oxidant radicals with a very deep potential. So almost any kind of organic molecule can be oxidized using this radical. On the other hand, if we have an oxidation reaction, naturally we need to have a coupled reduction reaction. The most important reduction reactions we are exploring are the evolution of the hydrogen evolution from water, and on the other hand, the reduction of oxygen, molecular oxygen dissolved in water to produce oxygen hydroperoxide radicals. These hydroperoxide radicals will perform oxidative reactions as well. And they can be used as a tool to perform this. So, a general picture of which kind of reactions can be performed using these semiconductors can be divided, and the main applications that we have for these semiconductors using the oxidative potential of the semiconductors. So we can list on them the treatment of contaminants, the biorefining of cellulose and other biomass, and the degradation of several pollutants. But on the other hand, we can use this potential to reduce things. And this potential to reduce things can include, for instance, the production of fertilizers in a very prospective manner, the production of renewable agroenergy, and the treatment of ag gases as well. Again, it's important to understand that these are two faces of the same coin. Means that we cannot do only one reaction, not taking into account the whole of the secondary reaction. For instance, we cannot do only oxidation, not paying attention in the reduction side of the reaction. We need to treat both at the same time, and sometimes means that we need to sacrifice one part of the reaction to improve another part of the reaction, depending on our interest. We have surveyed all these applications in this recent review paper we have published this year, where we tried to understand there the sequence of these applications in terms of technological emergency. I mean that technological emergency is how mature are these technological applications, and when we expected to see these applications along the time. You can see that the abatement of agriculture-related contaminants, for instance, pesticides, most of them are pesticides, but also hormones, veterinary medicines, and other contaminants like this, they have been they are under exploration since the 70s, the last century. But most of these technologies, although they are in a good level in terms of technological maturity, they are not still applied in a high scale. Other technologies, such as the fertilizer production, are in a very prospective scenario. We need to go. We need to understand more about these reactions and more how to produce it, how to perform these reactions to propose something applicable. But in general, we can explore these applications in terms along the time and understand that specifically in terms of the abatement of these agriculture-related contaminants, we have explored them because we have a real problem to address on that. The utilization of pesticides is growing with the growing of agriculture, with agriculture. So the production of the production of crops in the world is growing from the 90s, is growing in a remarkable rate, more than twice from the 80s today. But the consumption of the pesticides is going in the same way, is going in the same rate. Means that we have today more than 4 million tons of pesticides being consumed in the world today. And although the treatment of these pesticides in field is really complicated, it's a really complicated matter to do, it's not easy to address this problem after the application. On the other hand, we can concentrate our efforts in that situations where we have the pesticide in a concentrated manner. For instance, in the production of pesticides, in the washing of implements, in the recovery of water for human consumption, not for utilization in agriculture, and other examples like this. So, if we do a survey of the literature, you taking just checking the materials that have been used as photocatalysts for this kind of process, we see that we are still exploring, even in the last 5 years, we are still exploring titanium oxide as the most prospective material for this kind of application. We have revised more than 200 papers in the last 5 years studying the pesticide degradation, and we have seen that titanium oxide P25, the most common material used for this kind of application, is still the most studied material. But we can see that other variations of in the same topic, they are there. For instance, the end-doped titanium oxide, which is typically used to shift the band gap the band gap of titanium oxide to red, but also other similar materials, for instance, zinc oxide or tungsten oxide. Most of them are still used as batch molds, for instance, mixing these nanoparticulated materials in a tank with pesticide and exposing this directly to solar light, where these two reactions, the oxidation reaction performed by the production of weight radicals, are there taking place, oxidizing material, but also the oxidation, the reduction of molecular oxygen, making peroxide, is also playing a role. Again, the most important part is that the titanium oxide is doing the two in the two sides, in the reduction side and in the oxidation side, to radicals which are very oxidative radicals. Both of them can be explored. But this word cloud is also illustrative because we can use the same idea to understand which kind of material, which kind of substrate have been degraded in the last 5 years. And we see that the number of different substrates is too high. I mean, you can see from the chlorophenolic acid to glyphosate to other pesticides, methylperoxone, etc. But I see a specific concentration and triazinic pesticides, for instance, the atrazine, simazine, and other pesticides like them. This pesticide is among one of the most used pesticides in the world till today. It's used for corn production, and we know that we know that we have some typical problems in these pesticides in the aquatic biota, for instance, fishes and other fishes, frogs, etc. This is an example of one of these studies analyzing the concentration of atrazine in very, very low concentration levels, for instance, 30 ppb parts per billion in water. The influence of this atrazine in the body weight of fishes and in the ovary weight of fishes. These effects are well known. We know that they are associated to the disposal of this atrazine from corn production to the body water bodies closer to production of these crops. The problem that we have is that the oxidation of atrazine can produce a more toxic compound. This toxic compound, called the hydroxyatrazine, can have more effects on this biota than the pristine atrazine. Means that the treatment can produce a more toxic compound instead of producing not harmful compound. That's a problem that we need to address yet. And so the second problem is more critical problem is how these pesticides are applied. You can see this this idea. I found this idea, this picture in a. I found this picture in a procedure for dispersion of pesticides in oil-based compounds, and you can see that normally these pesticides, they are diluted in formulations with formulations using suspensions and using solvents. And so, in most of the cases, what we are trying to degrade are not pesticides in water, but actually a mixture of pesticides, mineral oils, some solvents, different solvents, making an emulsion. These emulsions, like this one, you can see here, this is the appearance of the pesticide before the application. A mixture of pesticide with a solvent and a soluble and a support oil. But this total white liquid is the appearance of the suspension. Means that I need to degrade much more than the pesticide itself. This is much more complicated to do than thinking in laboratory scale experiments, just dispersing the pesticide, for instance, in water, in the ionized water. And again, we have a second problem on that. The second problem is the limitation that we have in most of these catalysts to absorb only the UV light and not the visible light, which corresponds to most of part of the spectrum. And this is seen also by the sensitization effects that we have under visible light, which are well known by the people studying photocatalysis in general. And we can describe this sensitization effect as the absorption of a photon by the molecule, and this molecule injects this photon into the semiconductor. This is a general, a very simplified manner, a very simplified way to describe the sensitization effect. But this is interesting to understand how this affected the performance of the catalyst. This is a comparison of a paper we have published some years ago using one of these catalysts. This catalyst specifically is a carbon nitride modified with niobium oxide. And this carbon nitride modified with carbon nitride has been used to degrade a dye, which is optically active, means that it is absorbed. This dye is absorbing part of the incident light, and this incident light is converted in energy that has been transferred to the catalyst, degrading faster in that condition, in one condition with more carbon nitride in the composition. But when we try to do the same with a pesticide, in that case, amyloride, what we see is that the system is not optically active. And what we see in that situation is that the system, the system inverts the behavior. This is just a glance of what we can see about these effects, but this explains in a first moment that a good catalyst is not a good catalyst for everything, despite we have in some of these cases non-selective radicals. So we can extend this to other molecules, for instance, medicines that are used for the treatment of cattle, in different diseases of cattle. And you see again that the problem we have is how this pesticide, these molecules are dispersed in water and disposal water. You see, for instance, for these two medicines, propyzamide and paracetamol solutions, using deionized water and using drainage water, that the difference among them is perceived. In that case specifically, this is not too high, but in some of these cases, coming back to the idea of dispersion of oils or dispersion of surfactants and other components, the effect of these other components, these adjuvants, can be higher than the effect of the pesticide or the medicine itself over the catalyst. We can go in a more applied situation, and we can think not only in the effect of this oxidative role of the semiconductors over the pesticides, but use them as a pesticide. This has not been explored too much in the literature, but we found some examples in the literature. For instance, the utilization of some titanium oxide treated with silver and treated with copper ions over the surface to control the contamination of fungi over seeds. And this is very interesting to observe that this effect is clearly seen depending on the contaminant that we have in Italiana. Arabidopsis thaliana seeds in that paper, that leads to disinfection of the system in a good level compared, for instance, to the hypochlorite solution, which is a standard method. This kind of strategy might be interesting because we can use in that way a more stable pesticide, kind of pesticide, to control this kind of contaminations in field, compared to the hypochlorite, for instance, that's totally volatile and can be lost to the environment after some time. But again, going back to the time evolution of this prospective technologies, the second one is the treatment of aggregases. And aggregases, they are represented by a plethora of the different gases. You can see there in the IPCC report, the last IPCC report, a number of these possible emissions that are related to agriculture. For instance, CO2 is the most obvious of them, but other emissions are more important in terms of local effect, especially those emissions that are related with nitrogen, because these emissions have a more intense effect in terms of global warming. You can see that the emissions of nitrous oxide, they are too low compared with the emissions of carbon dioxide in terms of amount, but when corrected by the greenhouse, the equivalent greenhouse effect that they have, we need to multiply this amount of emission by 300, which means that we have the effect of 1 mole of nitrogen oxide in the environment is the same of 300 moles of CO2 in the environment. This is a huge number, means that we need to address this kind of effect, and we'll have a second effect on that. When we have the volatilization of these oxides to this nitrogen oxides to the atmosphere, they tend to react with water there and return as acids to the soil. So the most simple idea that have been proposed in the last years to treat these emissions is to try to treat them on the surface of roofs or concrete, treating them with a photocatalyst. That's really important. That's important to observe that the treatment of nitrogen oxides the nitrogen abatement can be done by the oxidation of these nitrogen oxides to nitrate ions, or by the reduction of these nitrogen oxides to nitrogen to nitrogen molecule N2. Both of them are possible. But normally, what we see in the literature is more effort in the oxidation of this nitrogen oxide to other more interesting forms of nitrogen oxides, and soluble nitrogen oxide forms. You can see that we have these examples in the literature. These examples are lab scale experiments using different nitrogen oxides that they are oxidized under UV light using titanium oxide again. But that's really interesting because we have some experiments that have been used in large scale in that specific case. One experiment like this one published some years ago has proposed the idea of making a thin film of titanium oxide over concrete. And the idea was to compare how the emission in that surface, in the emission in that surface close to the surface treated with titanium oxide, was different from a surface with no treatment. And we can see that through the behavior along the time, along the time of the nitrogen oxide is almost the same. The rates are almost the same. The levels are different. Means that we have a real oxidation of this nitrogen oxide, reducing the amount of NOx, X in the environment by a simple system that can be used in large surfaces. For instance, using roofs and pavements in general to treat this nitrogen oxide. Recently, some authors have proposed the idea to use the same strategy, mixing this titanium oxide with soil. But the idea on that was to oxidize these emissions before they are emitted from the soil. From the soil. The idea was to include these nitrogen oxides in the cycle of the nitrogen into soil, avoiding the emission of this nitrogen by the plants or by the plants during the biological process. Thought this is a very interesting idea. Actually, this is the only one paper I found in literature exploring this idea till now. This is still very recent, so we suppose that we will see more about this idea in the future. The second gas, the second gas with greenhouse importance is the methane. Methane is produced by the biodigestion. Biodigestion of any biomass will produce in anaerobic conditions. We produce methane as a byproduct. This byproduct can be used to produce energy, to be burned to produce energy. But again, we will have the emission of this methane now as CO2. It is less problematic than emitting methane, which has a very high CO2 equivalent CO2 potential. But on the other hand, we can use the photocatalytic application of several particles Again, the same titanium, the titanium oxide is a good example to oxidize this methane in a more controlled manner. Oxidizing this in a controlled manner, we can produce, for instance, carbon monoxide by the oxidation, by the controlled oxidation of this methane in water, or better, producing methanol. What's important on that is how to control this oxidation reaction, because this could not be done in a very fast manner, and we need to use some kind of sacrificial agent. And most of these papers, and most of the examples that we have in the literature, the hydrogen peroxide is the control molecule for the methane oxidation in a controlled manner. This controlled manner oxidation of methane, we have explored this in our laboratory using this very interesting catalyst, the carbon nitride, that can be easily produced by the concentration of melamine using melamine in temperatures around 500 Celsius degrees. This simple route to produce the simple route to produce this catalyst is interesting, because this gives us also a simple route to change the cations into the catalyst and modify them to more active catalysts, metal sites, to oxidize components, for instance. This product we have studied. We have studied in the first case for degradation of phenol. We have also studied the same system to produce methanol from methane. And we have seen a remarkable production of methanol using methane, saturated methane in water, using material with copper sites over the surface. Again, this is a totally photocatalytic experiment with no need of applied external applied bias, which means that we can produce we can use, in that case, if this is successful in the future, we can use an static process using, for instance, methane bubble in water to produce methanol instead of using methane for burning. The third gas that I want to focus with you is the hydrogen sulfide. Hydrogen sulfide is a characteristic gas related to the smelling of rotten eggs. This is typical from any kind of ripening you have in nature. Despite this is not greenhouse gas, it is not associated to greenhouse emissions. Specifically, this gas is an interesting source of hydrogen, and we still have problems with this gas, with the production, the side production of sulfur, of sulfate, that can be problematic in terms of acid rain, can be problematic in terms for degradation of implements and so on. This is an example. This is another example using manganese cadmium sulfide catalysts, where we can see that depending on the structure of this catalyst, we can accelerate the degradation using visible light, only visible light over the catalyst on that, the degradation of hydrogen sulfide to produce hydrogen. So we can think that this gas, in last term, can be a source of hydrogen. And this might be interesting to the potential of hydrogen. We don't know, we still don't know. But till the moment, the most important part of the treatment of this gas is avoid the side effects of the sulfur on that. So going back to the idea of the prospective applications, the third one we have seen we have in the literature is the biorefining. Biorefining is any kind of reaction that we are using over a bioproduct, so a biomass, biofuels, biomolecules, and etc. We don't need to close this in a very specific scenario, but one of the most important of them is the cellulose. Actually, cellulose is among the most used materials in the world, and the treatment of cellulose bleach is still an environmental problem. We found in the literature, we find in research several examples of the treatment of the cellulose bleach in laboratory scale, but we have some few examples of treatment of bioeffluents. And these bioeffluents are important to us because they give us more indications about the real problems that we will have if we decide to do these treatments in real life. You can see that even in that conditions, the examples that we have in literature, they are limited in conditions, limited in size. Few experiments are using, for instance, more than 1 liter of 1 liter of cellulose bleach in the treatment, meaning that we need to go, we need to do a lot of efforts, still a lot of efforts to make this viable as a industrial process. The second possibility is not looking on the cellulose, but looking in the looking for the applications for this, the most important byproduct of cellulose production, which is that is lignin. Lignin is a very interesting molecule to be treated using this kind of strategy because we can produce, for instance, formic acid by the oxidation of terminal groups of lignin and reducing the size of these chains, making other products that can be used before. Very important to see on that. The lignin is a very recalcitrant molecule. It means that the lignin is not easy to be reprocessed. We have some examples in literature, but the most important, the critical problem over lignin is how to separate after these products, such as succinic acid or acetic acid or formic acid, after a pulp of lignin, for instance. Anyway, the most studied of these byproducts in biorefining till now is the glycerol. Glycerol have been studied in different materials, the oxidation of glycerol have been studied in different materials, and you see examples in literature, for instance, the production of monoxide, carbon monoxide, methanol, CO2, methanol, methane, and hydrogen. Hydrogen, specific hydrogen, is a byproduct of the total oxidation of glycerol producing these products that you can see here. If you have the total oxidation of the glycerol, for instance, what we have here in the P25 platinum decorated P25 catalysts, what we can produce on that is a stream rich in hydrogen. And again, this might be a good strategy to reduce the potential, the necessary potential to produce hydrogen using solar light. Possibly, this is one of the most studied applications that we have for glycerol till the moment. And that production of hydrogen is a direct connection with the next topic. The next topic in our understanding is the production of renewable energy. You can see that the expectative application of this renewable energy is somewhat in the future. We don't have a clear number to say, but we understand that we are not working on somewhat that will be applied in the next 10 years, for example. We are thinking for somewhat for more than 10 years. But this production of renewable energy might be really interesting in terms of reutilization of CO2 streams, because we can use the same idea of hydrogen production by the oxidation of a product to reduce the CO2, and we have plenty of different sources of CO2, concentrated CO2. For example, this is the stream of CO2 that you can see in the ethanol production, which nowadays is producing almost 1 kilogram of CO2 per 1 kilogram of ethanol during the fermentation step, not during the burning of bagasse. This CO2 is a very pure CO2 with adequate amount of moisture, and could be used for the production of other products, such as an example. The number of different components we can produce using CO2 is reducing it to carbon monoxide, to carbon monoxide, formic acid, methanol, methane, among the other products. We can use this thinking only in C1 products, products with just one carbon, not products with two carbons. So we can think that in the future, we will cover, in the same idea, we will cover the production of other chemicals with higher molecular size. You see that the most important on that is how to cover these high potentials to reduce the CO2. And this potential is one strategy that strategy growing in literature to cover these potentials is the association of two semiconductors in the same particle. If I have, for instance, one semiconductor that has the concentrate all one of the charge carriers, for instance, all the holes or all the electrons, I can separate this process over the surface of the semiconductor, increasing the efficiency of the catalyst. We have two possibilities for that. For it, one of them is the so-called the Z scheme, which is the separation of charges by the utilization of a conductive layer among the semiconductors. So when both charges are promoted, both semiconductors are excited, means that we can transfer all the electrons from one semiconductor to conductors, while the other concentrate the holes. But the same happens when we have an electric structure, which is a system where we have the equalization of the Fermi levels of both semiconductors at the surface. In that case, the final effect is very similar. But the pumping of charges has a different behavior. I can use both of them with no distinction in that moment, and I will give to you an example we are exploring in our laboratory using semiconductor we are studying in our laboratory. The Renewable oxide. We have seen that Renewable oxide is one of the active catalysts to produce monoxide from CO2, using them in that same system, bubbling CO2 in water, in using this semiconductor as a powder dispersed in water. But at the same time, we have used this structure to support a copper oxide. This copper oxide over the surface is an interesting strategy because we can concentrate all the electrons in the copper while we have all the holes concentrated in Renewable oxide, separating both charges in that system. So, what we can see is that this separation can be interesting also to produce C2 compounds. In some situations where we have the covering of the semiconductors, not fully covering the semiconductor, we're using, for instance, only some spots of one semiconductor or another one, we can increase the production of CO2 molecules. For instance, in that specific case, the acetate molecule, acetic acid, which is interesting in terms of the total energy that we are storing in the molecule at the end of the process. So the problem we still have in that system is how to control the competition with hydrogen. We have studied, going back to the idea of carbon nitrates, which is one of the most studied materials in our laboratory. We have seen that different modifications over the system can lead to a very active system to produce methanol, but the modification with the system with cobalt oxide can lead to a system that is very active to hydrogen production. The difference among the both systems is that the system with cobalt oxide, only cobalt oxide, although this is still active to produce hydrogen, it is totally unstable. If this is totally unstable, it solubilizes during the process, making a homogeneous catalyst instead of an heterogeneous catalyst. But again, we need to pay attention on this kind of reactions because maybe in the future they will be worth of investigation both to produce hydrogen, or more interesting in the context of agriculture, sequestering CO2, making other molecules with CO2. Going to the very end of our presentation, I think that the most prospective application for this kind of reactions is the fertilizer production. In the very beginning of this presentation, I said to you that one of the most studied catalyst reactions in the world till now is the Haberbosch reaction. And this is actually a conversion of nitrogen to a fertilizer. We can do, in principle, this reaction we can do the same reaction in principle over the surface of systems that transfer electrons. Actually, the study of the coupling of nitrogen molecule over the surface of electrodes is really is giving some alternatives to modify to make the fixation of this molecule over the surface. And we have some advance in the last 5 years in this topic. But I want to remember to you that this topic is not new at all. Despite this is probably is gaining attention, really attention in the last 5 years. Actually, one of the first papers that has been published about the photocatalytic properties of titanium dioxide is from 1977, the last century, where the authors have observed the production of ammonia gas and hydrogen using a stream of nitrogen over titanium oxide, and in that case using UV light. So we have a long history about this, but the evolution of this research is only very recent. Going back again to the cloud of word cloud tool, we can do this over the database of papers published in the last 5 years, and we see that other structures other than titanium oxide are gaining attention. For instance, the bismuth oxobromide and the molybdenum tungstates are going faster. Why they are going faster? Possibly because they can produce some intermediates with nitrogen that titanium cannot produce. So we understand that in that topic, we are still in the catalyst discovery stage, because the yields, the production yields are still very, very low, too far from the necessary yields for fertilization. And also, we see that in literature, most of the research is still using electron donors, the sensitive utilization of electron donors. On other words, sacrificial molecules that can be oxidized to produce this nitrogen reduction products. So this is still there in the future, and we understand that we need to see there to foster this for our future, maybe something like 15 years from now, to see any application, any real application on that topic. But making some conclusion remarks about this topic, we have a good number of prospective applications, but we are still, unfortunately, in lab scale. We have, for instance, we have a lack of real effluent studies. Means that one of the most major technologies for utilization, the degradation of pollutants, is still limited by the lack of understanding on how to do this in real effluents. The second problem that we see is that we have fewer information about the photocatalyst stability in literature. We still have few information about the photocatalyst stability. Titanium oxide is still the winner, still the winning material. But limited to UV light. Means that even other materials that can absorb more from solar light, they can absorb more, but they don't have the same performance that titanium oxide has, absorbing only 7% of the total, 5 to 7% of the total solar light, incident solar light in the Earth. This is motivating more research in heterojunction research, in heterojunction with titanium oxide. You can see many of these papers, many of these examples literature, they are there in heterojunction. Environmental applications, they are in fact closer to the maturity, but they suffer from a low economic appeal. Means that many of these applications are not in the market in some of these cases because they cannot be put in clear numbers in terms of prices, how much they are interesting in terms of other conventional technologies that have been used to oxidize things. The emerging applications in energy, I understand that possibly they will go faster than the environmental ones because we have an energy crisis happening right now. So the interest in hydrogen, in the CO2 reductions is growing so faster in the market, in the world. So probably we will see more interest in understanding these applications than the environmental applications in the next years, in the coming years. I understand that this is a work in progress, and I need to acknowledge my group, the people who are working with me, my postdocs who are working with me in these several topics. Some of them they are studying more about the CO2, others studying more about other gases, and we have a good number of collaborators to keep covering covering this topic in the more wide perspective possible. As well, I want to acknowledge our financiers, the institutions, the foundations that are giving us support, financial support to keep us working this topic, and especially in to my institution, Embrapa, the Brazilian Agricultural Research Corporation. I invite everyone. I invite all of you, everyone who is in Brazil, to visit us here in São Carlos or visit us in one of our centers spread in the country. And specifically, I acknowledge the AgroNano Network, which is a network of research based in Embrapa researchers to explore this prospective applications for photocatalysis and other applications of material science in agriculture. I thank you so much. I'm open for questions. I'm open for questions today, but I'm open for questions by email or by other contacts in the future. I hope that we can collaborate in the future. Thank you so much.
Well, thank you very much, Caue, for your nice talk. It is really good to see the quantity and, more importantly, the quality of the research that you have been doing during the last years. It is also amazing to see the opportunities that we have in this field of energy, you know. While the audience write the question, I can start. I have a million questions, but I will start with only one. Well, Caue, you show in some slide that we are spreading chemicals on the floor, on the sea, on the rivers. And then when you show the image of a floor with titanium oxide, and you measure the level of nitrogen oxide, I was wondering if you could comment about the toxicity of the nanomaterials, because in several cases we are thinking of spreading nanomaterials to remediate the soil, for example. Can you comment, please?
Yeah, that's a really good question, Paulo, because this is a matter of concern. In fact, this is a matter of concern. When we are applying, for instance, the typical application of titanium oxide in field is somewhat in water is somewhat around 100 milligrams per liter of water. It means that if we are doing this in a water body, we have a significant amount of this contaminant there in this titanium oxide there in the field that should be recovered by some way to be reused, or should at least have no toxicity. We have studied, in the past, we have studied the effect of these nanoparticles in fishes, and we have seen that we have a small limit. We are still below this limit, this toxicity limit is still higher than the typical utilization of catalysts. But the problem that we have there is that the toxicity is different depending on the system, on the illumination of the system. This means that if I have the titanium oxide there in the water body, and this is in dark, the toxicity is really, really small, maybe not perceived. But when we have the sunlight there, the increase in toxicity is remarkable. This is a problem. So I understand that for the future, the most important applications need to address the problem of how to recover the materials after application. For instance, we can produce this titanium, this photocatalysis over magnetic particles to have a magnetic recovery after the process, or we can mobilize them over fluidized beds or other strategies like this one to avoid the contamination in the field. Afterwards, it's important to mention that most of these oxides, and this specifically happens with the titanium oxide, are not stable in low pH. So, for the treatment of drinkable water, what is done in that is using a step of treatment in bat mode, and after some time we stay with liquid 1 hour, for instance, 1 day, for instance, resting, and this is enough to reduce the amount of water. That strategy has been used in some parts in Africa, for instance, in South America, in some places for the treatment of contaminated water to produce drinkable water. Until the moment, we are in some safe levels of contamination. But I will insist on that. We need to do some more toxicological studies to understand how this can affect in long-term exposition. And again, other studies to recover this catalyst after application.
Okay, nice. And regarding to the same topic, I have another question. The use of nanotechnology, of the nanoscience in the industry is relatively new in a conscious way, let's say. So I was wondering if there are protocols, well-established protocols to study the toxicity of the application of nanomaterials in nature. Can you comment about that?
Good. We have an international effort. To do these procedures. Something important, Pablo. We are not. I understand that most of us we are not looking forward a new regulation paradigm. This is not the idea. The idea is not to produce a new framework to this, but include the concern about nanoparticles environment, to include this in the framework, the still existing framework for contaminants in environment. Means that we need to address, for instance, if we understand in the current framework, we understand that titanium oxide is not a contaminant, but understand how much this could be assumed as not contaminant with the particle size. Include this in the regulations, in the recommendations, not in regulations. It's important also to make a difference on that, because regulations is a political topic. The on the country means that each country needs to analyze the risks that they have using a product, and the recommendations are what we are able to do. We are able to do now is to write recommendations, for instance, to OECD, to other recommendations organisms regarding the utilization of these products. But this depends on the political decision of each country. Till the moment, what we have is just a modification of the current framework to include these nanoparticles, but not a totally new framework for to them.
No, great, Caue. Still a lot to do. And
Naturally.
if I may, I would like to add another question. You show different results for different systems. I was wondering in which scale do you work in your lab? And also, if you can comment something about the difficulties of the challenges to scale up the system that involve photo in
Great.
photochemistry or photochemistry that is easier in principle, I guess.
Yeah, we have a practical limitation. We have a practical limitation in the laboratory. We cannot do more than some milliliters of each system. Means that the maximum that we have analyzed in our laboratory is somewhat around 500 milliliters, a half liter, not more than this. But this is a practical limitation that we have in our laboratory. We have other examples. We have some examples of the treatment of pesticides in high scale. The most remarkable experiment is a pilot plant in Spain, in Granada. I don't remember the place. I can check the place after. But we have a big experiment in Spain. It is a station for testing of photocatalysts that is using an area of more than 1 hectare of mirrors to do the treatment. Means that we need to produce this catalyst in that size, and that's a big limitation. As far as I remember, the only photocatalyst produced in very large amounts is still titanium oxide P25 from Evonik. Is still the only one. We have other products that have been produced at some kilogram scale, in some gram scale, but not in that size. I mean, the only product that we can say today, if I want to buy 1 ton of catalyst, probably the only one that I can do for photocatalysis is titanium oxide. Okay, other products are in a prospective scale. Other products might be developed in further years, for instance, zinc oxide, because zinc oxide is used for other applications. So we can buy zinc oxide in a ton scale, but probably we don't have a product of zinc oxide produced for photocatalysis till now. We need to adapt to the products that we have in the market. This strategy was this problem is what is limiting us to do large scale experiments in most of these cases. Just a final example, we have tested 10 years ago, more than 10 years ago, we have tested to do the same same treatment like this treatment in an airplane company which was using spreading pesticide spreading in field. The idea was to treat all the pesticides that they recover in the production and treat these pesticides before disposal, because we have a specific regulation for doing that. But we could not do this in large scale, limited by 2 aspects. One of them was the first aspect was the limitation of available catalysts to be bought. In the second one was limitation in terms of operation hours. So this would be interesting for them to use just solar light, but solar light is 6 hours per day. 6 hours per day mean that I need to use other alternative to cover, for instance, the working hours with no sun. So this limitation has reduced the success of the alternative in that case. This doesn't mean that we are working with something something that won't get success, never will be successful, but means that we need to address these problems together with the application. We are not in a situation that we can do this in a very can do this with no addressing of the other problems.
Well, thank you very much, Caue. Really interesting. I want also thank to the live audience, but also to those that are watching this video in the future. Do not forget to do your inscription in our Cine Energy channel, and click on the bell to have the reminder of the next event of our Cine of Cine. Thank you very much to all of you.
Thank you so much for the opportunity, and I hope we can continue collaborating in these topics.
Bye bye.
Bye bye.